Hi guys, Sajjad Hussain again with a new video. In fact, this is not a new video, rather I can say it is in continuation of my last two videos. In my last two videos, what I did, I used this book, Seismic and Wind Design of Concrete Buildings. The buildings were based on 2000 IBC, ASC 798 and ACI 31899. And this book was compiled by S.K. Ghosh and David Fenella. And in this book, there was an example which inspired me. This example is something like this. It is a 12-story building with an overall height of 148 feet. In north-south direction, there are 3 bays, and in east-west direction, there are 7 bays. And this building is supposed to be in New York area, I think, where the zip code is 33122 and the seismic parameters are given as SS 0.065G, S1 is equals to 0.024G, site loss was D, and occupancy for the earthquake is 1. And the wind load or the wind speed was 145 mile per hour, exposure was B, and occupancy for wind was again 1. Dimensions were like that. The slab was 8 inch thick, beams were 24 by 24 inch, columns were 28 by 28 inch, and the shear wall was 12 inch thick. In my first video, I modeled this and I generated the seismic load by STAAD's seismic load generator. Let me show you. So here was the model and I used the STAAD seismic load generator and I used all these parameters to define the parameters over here, and seismic load was generated. And I checked and found that the seismic load generated by STAAD is in line with the seismic load calculated by the book. Then in my second video, I used the wind load generator of STAAD, and I tried to generate the wind load in both the directions. So in that case, what I did, I used parameters which I will be summarizing over here. So in x direction means the wind is blowing in east-west direction. It is blowing from left to right. So the building was considered to be category 2. There is a point that in IBC 2000, this is called category 1, but if I am using ASC 7, then it should be considered as category 2. The speed of the wind is 145 mile per hour. Exposure is B. Structure type is enclosed building. Overall height of the building is 148 feet. Length in the direction of the wind is 184.33 feet. Width perpendicular to the wind is 68.33 feet. Frequency was calculated for seismic case. It was 1.27 in this direction. Damping considered was 0.05, and of course occupancy was 1. Directional coefficient KD was taken 1 instead of 0.85. Then the windward load was calculated, or the generator, I can say, STAAD wind load generator was used. For windward conditions, the G was 0.97, CP was 0.8, and GCPI was 0.18. In leeward direction, of course, the gust factor remains the same, 0.97. The CP in leeward direction was 0.26, and for side wall the CP was 0.07 with a negative sign, and for the roof, since the roof is long in this direction, so there are three conditions: from edge to half of the height, which is 74 feet, CP was minus 1.14. Then from half of the H value to H, that is 74 feet to 148 feet, the CP was minus 0.78, and for the remaining portion it was minus 0.62. So using all these parameters, what I did, I defined the intensity in X direction, the windward direction, leeward direction, and the side wall direction in X. Based on these generated loads, I defined the wind load. In case of X direction, it was my load case number 6. The wind load in X, the windward, other face, side wall, and for the roof as calculated. And I took the most conservative value and I applied the load over here. Similarly, I defined for wind in case of Z, which is the perpendicular direction, and I defined the windward, leeward, and side wall loads, and load case number 7 was like this. Then I generated the load combinations according to ACI table, but then I noticed one thing, that in STAAD the oldest load code can be used was ACI 318-2002. In ACI 318-2002, the load combinations have a different factor than whatever is used in the book. And the book, the code combination was like 1.4D plus 1.7 live, whereas it is 1.2 plus 1.2D plus 1.6L, and with the wind also 1.6. So expected that the result will be slightly lower, but that's okay. The main issue was that we have to check the design of concrete beams and columns, and it should be in line with the calculated values. And second important thing was that the seismic load generated should be in line with the seismic load conditions provided by the book. During this calculation, I mentioned one more thing, that this building is designed as seismic category A. Because here it is clearly mentioned that exception 4 of IBC 1614.1 states that these structures located where SS is less than 0.15 G and S1 is less than 0.04 G need only comply with IBC 1616.4, which are design requirement for seismic design category A. And its base shear is calculated with a very simple formula, that is Fx should be equals to 0.01 Wx. So that means 0.0x is a factor which should be used to calculate the base shear. STAAD does the same thing. And when I use this word seismic design category, then the question arises that if this building is categorized as seismic design category A, then there should be B, C, D, E, F, G, H, I do not know how many. So How to define the seismic design category? So let us go back to the code and let's see how these seismic design categories are specified. Here is a table, table 1-1 in the same book. It says seismic risk terminology, and the seismic design category is divided into three parts. One where the seismicity is low, another one where seismicity is moderate, and in high seismic areas. Since we are following ASC 7, 02 or 05, so seismic category A and B is in the low seismic area. Seismic category C is in moderate seismic area. Seismic category D, E and F, these are in high seismic areas. Now, this is not going to solve my problem. Another question arises. So what is the difference between seismic category A, B, C, D, E and F? What I have to do? The answer comes from ASC 705. In ASC 705, we have a table, that is table 12.2-1. In this table, the first column is seismic force resisting system. So all possible seismic force resisting systems are listed over here. It's a very long table. Second column says ASC 7 section where detailing requirements are specified. So you have to follow this column to go to the relative detailing requirements, and you have to follow these requirements. In this table, we get the response modification factor R values, omega naught, which is the system over strength factor, and CD, which is the deflection amplification factor. And here are the seismic design category, that is B, C, D, E and F. Because for A, no special requirements are there, so that's why A is not listed over here. So still what the seismic design categories are. Let us go back to the seismic design category definition. Here we can see that importance factor is defined, and here as per table 11.6-1 the seismic design category based on short period response acceleration parameter. So value of SDS is there, and based on the occupancy category 1 or 2 and 3 and 4, we can check whether our structure falls under category A, B, C or D. Now the question is, where is category E and F? So category E and F are defined over here. That occupancy category 1, 2 or 3 structures located where the mapped spectral response acceleration parameter at 1 second period, that is S1, is greater than or equal to 0.75 shall be assigned to seismic category E. Occupancy category 4 structures located where the mapped spectral response acceleration parameter at 1 second period S1 is greater than or equal to 0.75 shall be assigned to seismic category F. All other structures shall follow the table. And there is one more table which shows for 1 second period, if the response spectrum falls in this range, then the seismic design category should be checked here, and the structure should be assigned the seismic design category. So in short, we have to check the seismic design category of the structure which we are going to design, and based on this seismic design category we have to provide the detailing. The example which I am following here, It is a seismic design category A structure. That means there is no special requirement. This is in very low seismic area. Basically, we can say that seismic conditions are not applicable. So only we have to design this building as per ACI 318. So what I did, I defined the parameters for concrete design. Code, as you can see, I have defined ACI 2002 and various parameters are defined. Nothing special, all the values are default. So let us run this. Let it run and let us see what is calculated here in this book. So after analysis and defining these loads, etc., of course I used to define the reduced values of moment of inertia, and I use these parameters. Now this is one example is given over here. They check the beam C4 C5. Here table 2.8 contains a summary of the design, bending moment and shear force for beam C4 C5 at the second floor level. Okay, so let us see what is meant by C4 C5 beam and second floor level. So let's go back to the model. C4 C5, that means we are talking about mid beam at second floor. Okay, let's see, run is complete. Let's select the second floor. So let us select the beam. So here is the C4 C5 beam, and this is on the second floor. Let's go to the post processing. Fine. Let's go to the beam and graphs. Let's see what is given over here in the book. So here what they have done, instead of performing a detailed analysis, they considered a tributary area and approximate analysis was done. And based on their approximate analysis, they calculated some shear force and bending values for various conditions. Since our case is little bit different, but anyway, so here they calculated that the minimum steel governs because the loads are not that much, and here they say the reinforcement is in the mid 3 number 7 bars, and at the support there are 7 number 7 bars. Let us see what is our result. Our result also bottom 3 number 7 bars, and here they are saying 3 number 8 bars or 5 number 7 bars, they are the same. So that means our calculation is also in line with the manual calculation of the book, which is presented over here. Thanks God, these are in agreement. Then they are calculating some reinforcement cutoff points. Of course, reinforcement cutoff point is not properly defined there, but you can see in the detailed analysis of the detailed result of the beam, they have defined the lap length, etc. We will see. So here the development length is calculated as 2.7 feet or 32.3 inches. Let us see what the result is given over here. This is our member number 371. Let us see the result 371 member number. Member number 371. Here is the result for member number 371. And we check that the support, the shear is given. As per the calculation, no shear T-depths are required, but we have to provide minimum shear reinforcement. They say provide 4 2-legged T-depths. That is standard. And on the other hand also, no torsional reinforcement is required, which is in line with the calculation, and same stirrup is also provided. So here we can see that on this end, where the reinforcement on the moment is high, they are suggesting 4 number 8 bars, or we can provide 5 number 7 bars over here. So that means our result is in line with the calculated values of as is specified by the book. Close this one. Okay. Yeah, sorry. Development length is in line with that one. Here is the figure showing, and of course this sort of curtailment is not over there in that much detail, but normally what we do, instead of providing that much curtailment and etc., we provide the throughout bar from one end to another end. Instead of saving by some amount of steel, we provide the steel and then save the work time. Then the column is C4, again between second floor, bending and shear on column C2. It should be C4. Load case number 3 and 4. That's okay, fine. It is between first and second floor. The column is C4. We will see which one is C4. Let's see the interaction diagram. Let's see C4 column over here. So it should be in line with A, B, C. somewhere it should be like this one. Yeah, okay. $275 or 455, the same thing. Let us see 275. So we will see what is the result for 275. These are all beams. $275, little bit late. Should be there. Here is 275. Reinforcement is something around 1.571%. Let's see what is there. Here they are giving a little bit higher value of reinforcement percentage, that is 2.59, which is based on their calculation and the difference in the load combination, etc. So that's why it shows higher value, whereas 1 to 8% is good enough, and our result is 1.57%. So we can say that this load is okay. The range is 1 to 8% as per ACI 1091. So it looks that the reinforcement is okay. Then if we see this interaction diagram, this value comes out to be P naught comes out to be something around 3,700, 3,800 or so, and our case what it shows, P naught 3,362 kips, which is in line with the values. And the balance is balance moment P MB balance, M balance is 1272. Here let us see what is M balance. Is a little bit higher, is more than 1500 or so. So that is, I can say we have already checked this. Our calculation for column is okay in STAAD, so I can assume that this is in line with the loads defined by us. So now I can conclude that at least for seismic category A structure, seismic design category A structure, the calculated reinforcement is in line with the calculated values, and we can design seismic category A structure with the STAAD. There is no problem at all. Hopefully you will like this video. Please do not forget to send me your comments if any, and do not forget to like my channel. Thank you very much. Bye.